Let's now talk about, what's required in order for a mixture to undergo phase separation, or equivalently, what are the rules or what are the conditions in which a liquid mixture will be in one phase and be completely uniform throughout. All right, and so the sort of thought experiment that we're going to go through is, let's consider that we have some sort of mixture, a binary mixture with two species, and we take the mixture from a very high temperature where everything is uniform, everything is in one phase, and we cool it down to a new lower temperature that will cause the system to phase separate. Okay? And so, just to explain some things, in the TX diagrams that I showed you before, for that upside down parabola line, the borders of that parabola, that's what we call the coexistence line. And so, similar to, in vapor liquid equilibrium, when you're on this line, this is where you could exist in multiple phases at once. Okay? All right. And so in our thought experiment, essentially, just to draw out the schematic, so say we're at some original composition x1, right? And so we're outside that coexistence line, and so that would mean that our mixture is in completely uniform throughout. It's in one phase. But then we take that system and we decrease its temperature down to here. And so now that we're inside the coexistence line, the system is going to want to phase separate. And as a result, the mixture will phase separate into two domains, in which one phase now has a composition of x1 alpha, and another phase has a composition of x1 beta. All right, and so that's that's the idea of what's going on. We could also do the opposite, right? And so let's say that we had a mixture at a very low temperature, that the two species didn't mix well and they phase separated. So we started here. But then let's say we heat the system to a higher temperature that's outside the coexistence line. Once we do that, we would see that the system would then become completely uniform, and we would just have one phase. So equivalently, let's say we mix two liquids that are immiscible at room temp. All right, and so let's say if you heat it to a high enough temperature, everything becomes miscible. But then that begs the question of, how high do you need to heat it? How high of a temp do we need to heat the mixture to get the species to be miscible? Okay. All right, and so to answer this question quantitatively and figure out, what that high temperature is, or even if you're interested, what are these compositions actually here, and where does this coexistence line form? The key to figuring all those things out is by looking at the delta G mix parameter. So the change in the molar Gibbs energy upon mixing. Okay. All right. And so essentially, to write it out in words, if you want two liquids to mix, then the molar Gibbs energy of the mixture needs to be lower then the combined Gibbs energy of the unmixed liquids, or the phase-separated liquids. Okay? And so that's what it is in words. Mathematically, that would just mean that your delta G mix, which is the molar Gibbs energy of the mixture, minus the weighted average of the pure species molar Gibbs energy, that delta G mix needs to be less than 0. Right? That's all this is saying. Okay? And so now let's think of a couple of different scenarios. So let's say our mixture formed an ideal or underwent ideal mixing. Okay? So then our molar Gibbs energy would just be equal to Xi Gi, the pure species, plus the entropy of mixing term. Xi ln of Xi. Okay? And so when we looked at delta G mix and we plug this in, this term would cancel out with that. Right? And so what we would be left with is just RT in the summation of Xi times ln of Xi. Okay? And so we have to remember that these mole fractions, can only be values between 0 and 1. Right? And we have a natural log of Xi here. And so for the natural log of anything that's between 0 and 1, that gives us a negative value. And since this is positive and this is negative, that means that for ideal mixing, our delta G mix is always going to be negative, or it's always going to be less than 0. Graphically, that would look something like this. And so on this plot, I have some examples of delta G mixing for different scenarios. And what we want to pay attention to is the bottom line here. Okay? And so for this case, when we look at delta G mixing and we look at it over the range from 0 to 1, it's always going to be negative. And we also see that as we go towards a mole fraction of 0.5, delta G mixing becomes more negative until it reaches a minimum at about 0.5. Okay? And so that's the sort of shape that you would expect for delta G mixing as a function of the mole fraction. Okay? Now, as I mentioned, if we go back to the notes, in order for two liquids to mix, the molar Gibbs energy of the mixture needs to be lower than the combined Gibbs energy of the unmixed liquids. Okay? And so another way we could think about that is that if we, had some original Xi value, and we wanted to see if it phase separated into, different compositions of X1 prime and X1 double prime, or something like that, what we would need to do is see, how the delta G mix at those different positions compare. All right? And so here's another schematic for the case where we have this ideal mixing, right? And so we have a curve that just forms like a parabola like that. And so if we take a look at delta G mix, and let's say we have it at some x1 value of our original mixture, what we could do, and this is the delta G mixed line, what we could do here is we could draw a tangent line that touches the delta G mix curve only at one point. Okay? And the reason for that is if we draw this line, essentially what we're doing is we're looking at the slope of delta G mix. Right? And if you remember from chapter 8, that the slope, or the partial derivative of delta G, or delta G over with respect to the moles of a system, that gives you your chemical potential. Okay? And so essentially what we're looking at here is the chemical potential of X1, or of species 1, at a composition mole fraction of X1. Okay? So we see here that we get some sort of minimum. So this X1, that's our original composition. So just ignore the prime here. Ignore that part. All right, and so let's say that's our original composition when we're in the one-phase window. And now we want to say that, all right, what at this temperature is it possible for this system to phase separate into compositions of x1 prime and x1 double prime? And so let's say those compositions would be somewhere here and here. All right, to figure out if that's possible, what you would do is you would draw another line that connects those two compositions. And we see that in this case, if we draw that line, we see that if we have a line connecting those 2 points, there's always going to be a range of delta G mixes that are lower than these 2 points. Okay? And so as a result, if there's a delta G mix that's always lower than these 2 points, then the system is going to want to go to those lower delta G mixing values, right? It's not going to want to stay at an energy level that's higher than the minimum that it could reach, all right? And so if that's the case, then what that would tell us is that it's not at these compositions here, the system would not be stable, it would not be at equilibrium, and it would want to drive itself towards the condition where it minimizes its delta G. Okay? So that's the idea there. That's if you have ideal mixing, then your system would always be in one phase, because that would be the lowest energy state.